Hello friends, I hope you guys are having a good understanding of the topics which I have been teaching through this playlist. Now let's look up to what Jacobian is and let's derive a Jacobian matrix. In this, we'll also be looking at the singularity of a manipulator. Let's quickly start with what a Jacobian matrix is. A Jacobian matrix is a matrix which links the Cartesian velocity with the joint velocity. Basically, it gives a function of the Cartesian velocity with respect to the joint velocity. And how are we supposed to do it? Let's look at it. But before that, we'll find out what a singularity is. A singularity is something which occurs when the joint velocity in the joint space becomes infinite to maintain the Cartesian velocity. How will we find it? Is through the Jacobian matrix. I'll explain it to you in further details within 2 minutes. Let's quickly derive the Jacobian matrix. So, if I say the Jacobian matrix is dependent upon the joint velocity and the Cartesian velocity, I'll write out the Cartesian velocity in respect to the joint velocity. If I assume that the joint velocity is dependent upon values of q1 and q2, then the joint velocities will be q1 dot and q2 dot. Similarly, the Cartesian velocity will be x1 dot and y1 dot. We will derive dx by dt in something like this form. That is, we'll find out dx by dq1 and then link it with the joint velocity, that is dq1 and dt. Similarly, how much has dx moved with respect to dq? And we'll find out it with respect to dq by dt. If we go ahead and find it for dy by dt, we'll have something like this. From this, we can clearly see that the formula, that is the comparison of dx by dt with respect to q1 and q2, can be expressed in the form of a matrix. How is this so? Look at this matrix. Here, we see that q1 dot and q2 dot are the velocities, and that is, they are the joint velocities. X dot and y dot are the Cartesian velocities. Through the earlier equations, we find out that dx by dq1 is what we got from the first equation, and similarly dx by dq is also what we got from the first equation. You go ahead and complete up the matrix. Okay, now one important point is the Jacobian also links up the torque and the force. That is, this is the formula. That is, the transpose of the Jacobian matrix links the force and the torque. Okay, so what I was explaining to you earlier, that is the respect of singularity with joint velocity and Cartesian velocity. I said that the joint velocity becomes infinite. That is, we have to make the Jacobian matrix as 0 in order to find out the singularity of the matrix. Okay? So, this is what you can find out from the Jacobian matrix. That is, you can find out the relation of the joint velocities and the Cartesian velocities. You can also find the relation between the torque and the force. And you can find out the singularity of the manipulator. Now, let's quickly look at an example. Okay, we are looking at a manipulator with endpoints r cos theta and r sin theta, since it's a r manipulator. That is, it has one joint which is rotational joint. Okay, looking at the formula which we derived earlier, we say that the rotation takes place with respect to r and also the theta. That is, the first q1 will be a relation with respect to the r. That is, dr cos theta divided by dr with respect to dr by dt, and dr cos theta divided by d theta. Since it's with respect to theta, we'll multiply it with d theta by dt. I hope you are understanding it. If you have any doubts, please comment below. Similarly, for y, we'll find out y dot equals to the same way we derive this, and we'll come up to something like this. if we put the values of the equation into a matrix, we'll find out the Jacobian matrix of the R manipulator. Now let's put up the values. We know that the dx by d theta over here is minus r sine theta. How is that so? Because we have specified the Cartesian velocities to be theta dot and r dot. So for the first row, first column, we have to find out the relation of dx by d theta. That is the value of minus r sine theta. If we look at the value of dx by dr, we'll come up to the formula of minus cos theta. Similarly, put up all the values and you'll find the answer. If you go ahead and find out the singularity of this matrix, we see that determinant of J should be 0. You go ahead and find out the value of the determinant J equals to 0, and please comment your answers below. I'm eagerly waiting for your answers. Let's look at the last question for now. That is Jacobian and singularity of an RR manipulator. It's a very important concept. Since we have already seen that we know the values of x and y, that is the endpoints of an R manipulator. In the RR manipulator, we don't know the values, and since we don't know, we derive it through the forward kinematics. If you remember the answer of the forward kinematics of an RR manipulator, I'm really proud of you. You can go ahead and plug it in. That is, the value of x is C1 L1 plus L2 C1 2. That is cos theta 1 L1 plus L2 into cos theta 1 plus theta 2. If you go ahead and derivate it with respect to theta 1 and theta 2, since we have two revolute joints over here, we find out something like this. You go ahead and find out the values of y and y dot. When you plug this whole values of the Jacobian matrix, the matrix will look something like this. This is a very important matrix. This is the Jacobian matrix of an RR manipulator. You know how I did it. That is, I put the coefficient of theta 1 dot over here, theta 2 dot over here. And for y dot, I put the values of theta 1 dot over here and theta 2 dot over here. Now let's find the singularity of this matrix. We know that for singularity, we need to make the determinant of the Jacobian matrix to be 0. When you do that, when you find out the determinant of Jacobian matrix of RR, the value is L1 L2 S cos theta 2. The value will be, that is the value of theta 2 will be 0 or 180 degree. Here we find out that the 0 is the internal singularity of the matrix, and theta 2 value when it is 180 degree, it's the boundary singularity. That is, it should always be in between of 0 to 180 degree. And think I forgot to tell you guys the value of L and L1 is the link length over here, which I have made it as constant. In the earlier question of R, it wasn't, and that's why it could move R cos theta and R sin theta. I hope you guys understood. If you guys have any queries, please comment below, and I'm looking forward for your answer on what I had asked you. Thank you. Robometrics.